Hi friends, here in this video I'll be explaining a problem on closed system. So let's get started. Now here is the question which is given. It is said a system contained 0.2 meter cube of air. So the volume of air is given. Whatever is there in the question, I'll write that in the form of data first. So let's get started. And here in the data, volume V1 is given, which is 0.2 meter cube. And the working medium is air, mentioned in the question. Then at a pressure of 4 bar and 160 degrees Celsius, so initial pressure and initial temperatures are given. 4 bar pressure, I'll convert it. It is 4 into 10 raised to 2, that is 100 kilonewton per meter square. Then the initial temperature is 160 degrees Celsius. Adding 273 in it will give me the value in terms of Kelvin, and that is 433 Kelvin. So convert the temperature in terms of Kelvin, that is absolute temperature. Next, expands isentropically to a pressure of 1.06 bar. So here we can see there is a pressure drop from 4 bar to 1.06 bar. It means it is an expansion process, and that is isentropic expansion. So it is an isentropic expansion which is given by the law PV raised to gamma equal to constant, that is C. The pressure is falling 1.06 bar. So when I convert this, it is 1.06 into 10 raised to 2 kilonewton per meter square. Then, and after this, the gas is heated at constant pressure till the enthalpy increases by 65 kilojoule. So after reversible or adiabatic, or we can say isentropic expansion, there is constant pressure heating. Now the process starts from state 1, that is from P1 to P2. Here we get the expansion, pressure drops, and then constant pressure heating is starting from pressure P2, it continues up to pressure P3. So we can say that P2 equal to P3, that is the constant pressure heating. Next, and the enthalpy increases by, it is given as 65 kilojoule. So that is the change in enthalpy denoted by delta H, capital because the value is total, that is in terms of kilojoule. It is not in terms of kilojoule per kg. So the value is total enthalpy denoted by capital H, that we have to remember, 65 kilojoule. Next, calculate the work done. So we have to find the work done, that is the question, during this processes. Then it is said, and now imagine that these processes are replaced by single reversible polytropic process. So that is another part of the question. So at first I am going to solve only up to this work done, and the remaining part we can solve it as the other part of the question. So the first part, and in the end they have given Cp for air is 1.005 kilojoule per kg Kelvin, that is specific heat at constant pressure. Second part I am going to solve. Now starting with the first part, we have to find out the amount of work done. So into the solution, I'll give it as case number 1. Calculation of work done. And for that, first I'll draw the PV diagram. So here I'll be drawing the PV diagram, and as we can see, at first it is isentropic expansion. So this is state 1 and here is state 2. At state 1 the pressure is P1, at state 2 it is P2. And now, since for constant pressure heating, we do not know that either constant pressure on this PV diagram is indicated with a horizontal line. So either we should go horizontally towards the right or towards the left. So to decide that, I'll explain that we can use this equation, which is PV upon T is equal to C, in order to decide that the process goes in which direction. And now here it is a constant pressure process, so therefore V upon T will be equal to, C will remain as it is, P would be shifted, so C upon P is another constant, that is C dash. So I can say that therefore V is equal to C dash into T, and when I remove this constant, so we have the proportionality sign. Now volume is directly proportional to temperature, and since it is given that it is a constant pressure heating, so the temperature will go on increasing. So when the temperature increases, the volume also increases. So it means on this diagram I have to move towards the right in order to increase the volume. So this is a constant pressure heating process indicated on the PV diagram. So pressure P2 equal to P3. Now whatever the area which we are getting under this PV diagram, that area is nothing but the amount of work done. I'll just shade this area. So whatever the area which we are getting under this PV diagram, that gives us the work done, and as we can see here, the volume is V1 initially, then it becomes V2, and finally the volume is V3. Now the question is we have to find the work done, so I'll say that therefore the total work done is given by work done during process 1 to 2 plus work done during the process 2 to 3. Keeping this as the first equation, and here 1 to 2 is indicating isentropic expansion, so that is denoted with the law PV raised to gamma equal to C. Next, therefore work done during process 1 to 2, which is the reversible adiabatic process, or we can say isentropic process, it is given by P1 V1 minus P2 V2 upon gamma minus 1, and this same can be written as, also the formula is given by, instead of P1 V1 and P2 V2, I can write it as MR T1 minus T2. This I am keeping it as equation 2. Why? Because since PV is equal to MRT, so P1 V1 has been replaced with MRT1, P2 V2 with MRT2, so MR is common and it is T1 minus T2. Now when we look into the data, T1 value is known to us, similarly P1 and P2 are known, the only unknown is T2 and also the mass. And remember, here I am explaining a point that whenever for a particular state, like for example for state 1, P1, V1 and T1 are given, these are the hints. Whenever initial pressure, volume and temperature all are given, try to get mass first, that is the mass of air as it is mentioned in the question. So here I'll say that after equation number 2, and in order to calculate the mass, use the characteristic gas equation. So therefore from the characteristic gas equation, which is P1 V1 equal to MRT1, so therefore M will be equal to P1 V1 upon RT1. Pressure P1 is 4 bar, that is 4 into 10 raised to 2 kilonewton per meter square. Initial volume is 0.2. R value, now since pressure is in terms of kilonewton per meter square, R should be in terms of kilojoule per kg Kelvin. So the standard value for air is 0.287 kilojoule per kg Kelvin, and temperature T1 is 433 Kelvin. Here I can write down, assuming for air capital R is equal to 0.287 kilojoule per kg Kelvin. That's the standard value. If in terms of joule, that would be 287 joule per kg Kelvin. Now on calculating this, the answer of mass will come out to be it is 0.64 kg. Then in equation 2, when we see here, when we are calculating the work done during process 1 to 2, T2 is the unknown. So for that I can use the relation for the isentropic process, and that is for process 1 to 2, that is reversible adiabatic or isentropic process, T2 upon T1 is equal to P2 upon P1 raised to gamma minus 1 upon gamma. That's the standard relation for an isentropic process, and therefore T2 is what we have to calculate. T1 is given, it is 433. Then the pressure ratio, P2 is 1.06, P1 is 4. Now since it is pressure ratio, so either we keep it in terms of bar, Newton per meter square or kilonewton per meter square, it won't matter. Then gamma value for air is 1.4. On calculating this, T2 comes out to be, it is 296.28 Kelvin. Now once T2 is also known, I can say that therefore put all values in equation second. So therefore in equation 2 we have work done during process 1 to 2 is equal to M into R. So M value is 0.64. It is MR T1 minus T2 upon gamma minus 1. So M 0.64 R. Now if I keep R in terms of kilojoule per kg Kelvin, the answer of work done would be in the form of kilojoule. So therefore R is 0.287. Then it is T1, which is 433 minus T2 296.28 divided by gamma, which is 1.4 minus 1. So hence the answer of work done comes out to be during process 1 to 2, it is 62.78 kilojoule. And why it is in terms of kilojoule? Because the mass is not 1 kg. Next, similarly, I'll be calculating the work done during process 2 to 3. So therefore work done during process 2 to 3, which is a constant pressure process, work done is given by pressure into the difference in volume, which is P into V3 minus V2. So therefore, and how we can write this is that, because when we see the constant pressure process, this is the area which we have to get. So the height is corresponding to the pressure, and this distance is V3 minus V2. So I have to find the area of this rectangle, and that rectangle is having a height of corresponding to pressure. So I am writing it as P. It can be either P2 or P3. So we can say it is, for example, P2 into this difference, which is V3 minus V2. So here when we are calculating this, it is P into V3 minus V2. It can also be written as MR T3 minus T2 in a similar manner, because it would be P3 into V3 and P2 V2 pressures are constant. So we can write MR T3 minus T2. Now I am keeping this as equation 3 because we don't know the value of T3 here. For that, in the problem they have given a data which we can utilize, and that is the change in enthalpy. Remember, change in enthalpy, whenever they have given in the problem, it would be used in order to calculate the temperature. Any of the unknown temperature can be found out by using the change in enthalpy formula. So I can say that therefore the change in enthalpy is given by delta H is equal to mCp, the general formula, into T3 minus T2. Now in this formula, delta H is known to us, mass is known, Cp for air is 1.005 already given in the problem, kilojoule per kg Kelvin. T2 is known to us, so T3 can be found out. So I can just go on putting the values here. Mass 0.64, Cp 1.005. So T3 comes out to be 397.34 Kelvin. Then putting all values in equation 3, we have work done during process 2 to 3 is equal to, it is m into r into T3 minus T2. So m is 0.64. R I am keeping it in terms of kilojoule per kg Kelvin, so 0.287. In order to get the answer of work done in terms of kilojoule, then it is T3 minus T2. T3 is 397.34. T2 is 296.28. So therefore the work done during process 2 to 3 will come out to be, it is 18.56 kilojoule. Now both the work done are known to us, that is work done during process 1 to 2 and 2 to 3. So I can put their values in equation 1 in order to get the total work done. So after this, put all values in equation 1. So therefore the total work done is equal to, work done during process 1 to 2 came out to be 62.78, plus during 2 to 3 it is 18.56, and it is 81.34 kilojoule. Now that's the first answer. And whenever we are getting the positive answer of work done, it means it is work done by the system, that is we are getting work from the system. And now I'll read the second part of the question which was left. It was said that, now imagine that these processes, here there were two processes, reversible adiabatic, that is isentropic expansion, and constant pressure heating. So replacing them are replaced by a single reversible polytropic process. So replace both these processes by a single polytropic process, producing the same work between the initial and final states. So we have to keep the initial and final states. Initial state was state 1, final state state 3. So we have to keep the state same, means the values of pressure, volume and temperature at those locations 1 and 3 will remain same. And find the index of expansion. Take Cp for air as 1.005 kilojoule per kg Kelvin. So the index of expansion for the polytropic process is denoted by, that is small n, the polytropic index which we have to calculate. So this would be the case number second. So I'll say that therefore case number second would be, calculation of polytropic index n. So again drawing the PV diagram between the states 1 and 3. Pressure is P1 and here the pressure is P3. Volume is V1 and here it is V3. And whatever the area under this graph is there, that gives us the work done. And this work done would be for the polytropic process, which is given by the law PV raised to n equal to constant. So the condition is we have to keep the work done as same. Keeping the work done as same, find the polytropic index. So I'll write down that since work done for a polytropic process is given by it is P1 V1 minus P3 V3. Instead of gamma, here we have N, polytropic index. And as we can see here, like in case 1 there were two processes, isentropic expansion and constant pressure heating. Those have been replaced with a single polytropic expansion process and producing the same work. So therefore the same formula can also be written as Mr T1 minus T3 upon N minus 1, and here is the work done, polytropic. So therefore I'll put the value of the polytropic work done, which is 81.34. Mass would be same, R is 0.287 kilojoule per kg Kelvin, because here work done is in terms of kilojoule. Then T1 value was 433 minus T3 value, which was 397.34 upon N minus 1. So from this the value of N will come out to be it is 1.08. That is the answer of the polytropic index. So it means when we have replaced both the processes by a single process and the process is a polytropic expansion process, so the index comes out to be 1.08, and with that the problem gets completed. That is, whatever the questions were there, we had solved them, and that's the end of the problem. At the end, if you'll find my videos helpful, you can like, share, comment and subscribe our channel and share it amongst your family and friends. Thanks for watching.